Good morning, everyone. This is Dave Kroll again. We have the next in our masterclass series with Bryan Sydnor, who's a graduate student at Cal State Long Beach. He's also an engineer at a major aerospace company. Bryan's one of those people that I've considered to be one of these natural simulation modelers. He just has a real knack for it. So he's built a number of fairly complex models. He's one of our main beta testers and feature suggesters. So with not much more introduction than that, I'll turn it over to Bryan.
Hello, my name is Bryan Sydnor. We're going to walk through here ConOps, the concept of operations, modeling, and simulation. There we go. A little bit about my background. My background is in a Bachelor of Science. I've got in mechanical engineering with an emphasis in applied math and technical theater. I studied at Drexel University in Philadelphia, and while at Drexel, I got an internship out in California and subsequently moved to Cal State Long Beach, moved to California and finished out my degree at California State University in Long Beach. Currently, I'm working on a Master's of Science in both Operations Research and Applied Statistics at Cal State University at Long Beach, and I've been an ExtendSim user since 2008, which was version 7. Kind of give an introduction into what ConOps modeling and simulation is. Concept of operations has been defined in two general forms, both in military doctrine and by the IEEE IT guideline. In the military doctrine, it's defined as a verbal or graphical statement that clearly and concisely executes what the Joint Force Commander intends to accomplish. In the IT guidelines, it's a user-oriented document that describes the system characteristics for a proposed system for the user's viewpoint. The ConOps document is used to communicate the overall quantitative and qualitative system characteristics of the user, buyer, developer, etc. In general, what a ConOps is what is the objective and how to achieve the objective. And there are two basic aspects of ConOps modeling. You're either looking at the minimization problem statement or the maximization problem statement. In the minimalization problem statement, we're looking for the amount of equipment, spares, fuel that might be needed to ensure a minimum amount of downtime. In the maximization problem statement, we're looking at the maximum amount of material that can be processed, packages, and or searchable area that can be executed based off of a certain concept of operations. As part of this master series, we're going to look at 3 areas. How to use Excel to drive ExtendSim model behavior, the methods and applications of the query equation blocks, and model control and measurement. Looking at modeling philosophy, a couple of things with regards to modeling philosophy. Building a model is often communicating. Building a model, it is important to understand communicating model intent. And as part of that, the way we select blocks and the way we orient blocks, we can help communicate what our intent was, and this helps the knowledge or transfer of knowledge from one modeler to the next. In the graphic that we're seeing here, both the create block, the queue, the activity, and the exit block are the same in both situations. In the top row, embedded in the activity is the distribution, the units, and all of the information associated with that activity. When creating simple test models where we're working with one modeler and working by themselves, this is often the most efficient way of building models. But when looking to transfer knowledge between multiple modelers, in the second set of create, queue, activity, and exit block, we see that the use of the random block and the use of the units block helps communicate to someone else opening the model that the information about this activity was collected in November of 2011, and it was specifically collected in hours, and it is being converted to model time in terms of this model. So how we pick blocks can help communicate our intent from one modeler to the next. The other thing about modeling philosophy is creating a model is as much art as it is math science, and technology. And on the right-hand side, I've laid out kind of the flow diagram. This is one of the common flow diagrams in Introduction to Simulation Modeling of what are the process steps required to go off and build a successful model. One of the most important things is setting the objective and overall project plan, and understanding the verification and validation plan, and making sure that the design of experiments, or what experiments are going to be done, are absolutely critical. Those three areas will often drive a lot of the schedule time in developing a model. Looking at some of the major elements of concept of operations modeling, sequence of events. In a sequence of events, you have basically the necessary sequence of events to achieve the objective. What are the steps that have to happen to ensure that the objective is made? There's a sequence of interrupts. What are the unplanned or planned events which will interrupt the sequence of events? This could also be considered an MTBF, where a unit has failed, and along those lines, something that is unplanned for within the sequence of events. The shorthand notion is SO, E, and I. And then the third area we're going to look at is measurement techniques, both utilization and consumption, where utilization is the percent used, the percent time used over the percent time available, and that is a time-dependent measurement. And then also the consumption, both looking at the consumption rate, using the rate blocks to measure consumption. There are other techniques using the information block, and then also summation blocks that will allow for the for measurement techniques. When creating the sequence of events and interrupts, in models where the SOEI are small, creating the structure can be done very simply using item blocks, items, and or H blocks. But where the sequence of events start growing in size, looking at other ways to execute them becomes necessary. Oftentimes, if this sequence of events is over 10 or 20, building them from model elements becomes ineffective. And at that point, looking at other options, such as using the ExtendSim database, simplifies this model development. Extend offers a plethora of both internal and external ways to create the database, to create and work in databases. Both Extend has a very extensive internal database, as well as it allows you to read and write from Excel, ODBC databases, both FTP and also text sites. This allows the model architect, or external sources will allow the model architect to solicit inputs from a much larger organization in order to execute the model correctly. When using Excel, I have found that using multiple input sheets to the different stakeholders, and then creating one large model transfer sheet that allows for the data to be transferred over in one lump sum allows for a much more cohesive interaction amongst the organization. I'm also going to look at a couple of things. One can also use Excel in and of itself to actually drive the data location inside of Extend. I'm going to show that. So let's look at two models right now, both the basic way of loading in data from Excel and then some Excel-based loading. So Excel offers, or excuse me, Extend offers two ways to import from Excel. The input file, the import data and export block found in the item library will allow the user to input and export data from Excel. The three main items on the import-export, where it's imported from, where it's importing to, the file name, and where on the sheet it's located. On the Options tab, specifying the range in which the data is located is also critical. There are two ways to do that. either setting just the upper left-hand corner, both row and column, in which case the data that's being loaded in will fill up the entire database that has been specified to. So when we import this data, we specified the upper left-hand corner in this data, and it brought in all of the data. Note that in this database, there was data that we did not want to import from Excel. In this case, setting up both the upper and lower bounds on that data, when you import the data, even though present in Excel, is not going to be loaded into Extend. This allows for the model architect to specify exactly how the data is being loaded into Excel. In this model, we also see that there are 4 stations. Each station represents one item in the sequence of events necessary to execute the model. And as part of that, we have the sequence of interrupts here, which is basically a measure of yield on each station. The yield then feeds back into the station that it was processed. In the second option, the model transfer sheet contains a little bit of extra information. It contains the start and end rows of all of the data that's going to be imported into Extend. This is done by identifying the lower right-hand corner and the upper left-hand corner of the data. The reason why this notation is one over from the data is Excel always forces inserts to happen to the left. This allows this to move, allowing new data to be brought in. This tab here also then has to specify exactly where the data is being loaded from. In the Extend, the import is broken up into 2 steps. The first step of the import is on the Options tab. It's done during pre-check data. What that does is that actually that imports during pre-check, during the message sent out by the executive block during pre-check data. That imports the data location for all the data that's going to be imported, at which point the equation block allows us to run the equation block at check data, at which point the data is being evaluated. The data is being evaluated, and the number of records is being either added or deleted, is either inserted or deleted from the database, depending on the size of the input tables specified. And then the third aspect necessary here is the data import from the specific tables that have been defined in Excel. The locations have been linked. Each one of these have been used using a link dynamic, a dynamic link property linking to the cell location inside of the data table, representing where the data can be found. When we run this, the total number of stations in the data, 5 total stations were added. And we can see here in the model that the stations 6 were the ones that left the system. We can either remove or add a station. So in this situation, let's remove this station. So by deleting this station, coming back into Extend, rerunning the model, the number of stations now went to 5, and we'll see that the only items that have left the simulation are stations that are exceeded the number of 4, which is 5 left the simulation. These 2 options allow the model architect to build models that will execute a sequence of events, allowing for interrupts as well. One of the things that has to be noted that in the previous model, each station had its own queue. In this specific environment, the stations were updated to be 5, and this queue was sort of just first in, first out, which truly isn't representative, and we're going to come back to that later in model control. One of the blocks that provides a very powerful way of controlling the model, and it's my understanding that it is an absolutely unique feature to extend. I haven't seen it in the other modeling tools that I'm out there right now, is the query equation block. What the query equation block does is it does something very unique. For each record within an ExtendSim table, the equation is executed. From that execution, one of the outputs needs to be the database query rank result. The output variables for each record are stored in memory and then sorted by the DBQ record rank. The winning record's output variables are then posted to the output connectors or stored in attributes. They're stored in the output variables. One can select what the winning rank is by either the highest record rank, the lowest record rank, or the first true record rank. And when they say first true, true is a value of greater than 0.5. There are two special features with the query equation block. Both the query equation value and item has the capability to write to the beta database as it is stepping through each record. This is independent of the values that are stored on the output variables. Because the equation is calculated for every record, as part of that record calculation, a db data set command can be used to set a value into that database. In the equation item block, there's also another special behavior, and it is called spawn. In this situation, every true rank or the first true rank, an item will be created. This is with the item only, and there is a special rank result called the DB spawn query, DBSQ record rank, and it is used to indicate a spawned record. Also, in the spawn situation, you can have both a DBSQ, which is a spawned result, and a DBQ that is being used in the same block. This helps indicate there are two items in the query equation block when it is spawning. The pass-through item, which is the item coming in initiating the DB query, and the spawned items. The spawned items represent the DBSQ, and the pass-through item on the output variables are represented in the DBQ. Quick extend model on how this works. So in this model, we have two query equations. We have the query equation value and the query equation item. In this model, as the item comes in and is triggered, the go connector here is triggered by an item passing using the get block. In this situation, the code that's being executed is twofold. For every value that is greater than the test value, walk through the inputs. The DB read queue value is reading the value from database 1, item status, database 1 and item status, The DBQ, which is the database query read value, it is the variable name is value, and it is reading it from the database location of 112, which is these values right here. The database query current record index is going to be used to indicate what record we are currently being processed. The in connector is the test value that we're using, and the DBQ read value is we're also going to read the output value, which is this field right here. As the equation is being executed for each one of the 4 records, the equations are going to step through. The first thing that it's going to happen is it's going to write a value for every record in the database. If the test value, if the value in the test value in the database here and the incoming value test is greater than, the check mark here will go high. It will go true on the check mark, and this is what's the DB set as number in the 111 current record, and the value of 1 is being set. The second thing that it's also doing is it's setting the rank result. When the value is equal to test, it is setting the rank result. Otherwise, it's setting 0, and the output connector is being stored at the output value. In this case, when we run the simulation, we can see that for a test value of 3, all the test values less than 3 were checked true, and the winning rank was 3, and the value of 11 is being presented on the output side. As this is being changed, if we were to change this value to 1, we would see the behavior change in the simulation, where only 1 would be checked, and the output of 3 is being shown. Secondarily, the query equation item is being used, and in this case it is being used to spawn items based off of all true ranks are being spawned, and the pass-through item always passes. In this case, we are reading the DBQ value, and we are reading the value of this first field. If the value of the first field is true, the DB spawn rank result is being set to 1. If not, it is being set to 0. So based off of the number of true values here are the number of spawned items that are going to be created. So we can see in this situation when we change the incoming to 5, we see that all 5 get checked yes, and we see that 5 values have left to spawn. Also in this case, the pass-through item has left. There are options with regards to the pass-through item. We can never pass it. In this unique situation, when the item enters in and executes the DB spawn, the query equation with the spawn connector selected, the pass-through item is deleted, but the spawned items are then created. This allows the user a high degree of variability or versatility when using the DB query both value and item inside of a model. There are some multiple situations in which the DB query block item can be used. The 3 major ones that are currently being used for, it's being used in the service time or MTBF models, where as a vehicle operates, there is an MTBF across multiple different components in that vehicle. In this case, the sequence of interrupts would be considered the subsystem name, and all the subsequent associated MTBFs for the subsequent MTBFs for all the different subsystem components. There are order generations, looking at ConOps where one is looking at an inventory system and looking for shipping and sales. This can be handled in one of 2 ways. This can be handled both if we're looking at an Amazon-style model, where there is a large set of inventory and there are orders being come in, how to structure or build warehouses that will handle those types of orders. There are also, order generation can also be treated in the case of FedEx or UPS style model, where every day a certain number of packages are created that have to be handled and shipped across the country. And a lot of these models can be built off of the current data that is available within their databases. The third area where the query block has a lot of uses are in search and detect models, where you use the query block to represent an interrupt. If there is something in an area, and will the probability of detect capture it. In an MTBF and repair time modeling, the MTBF and repair time modeling techniques primarily require two data locations. The first data location is the performance characteristics of the model elements. This, in many cases, would be the sequence of interrupts associated with a sequence of event model. The second thing that has to be kept inside of the model is the current number of model elements within the system and their current status. So if we're looking at an airplane, for example, the performance, the MTBF on the airplane, looking at all the different components within the aircraft, as well as the service time on all those different aircraft, and then subsequently, what is the status of each aircraft as it works through the simulation. There are four major elements that need to be focused at in an MTBF or repair time model. The initial model elements. This can be represented using the resource item. How many aircraft do we have in our fleet? How many trucks do we have in the UPS model? So on and so forth. We also have to store two bits of data. We have to store the model element status, and that can be done using a database. And then we also have to evaluate the current model status, and in that case we want to use the query block. And then we have to execute the outcome. So in the case where there is an MTBF, or we've exceeded the repair time on a subsystem, we then execute that outcome, either preempt the vehicle in transit, or prevent the vehicle from leaving transit if the forecasted trip will exceed the repair time on a certain subsystem, forcing it into a repaired status, and then reconvening that at the end. And to do that, both the batch and or queue matching blocks can be used to reconvene both the repair item and then also the original model element, such as the aircraft or the vehicle. In an order generation environment, two data locations are necessary once again, both the customer list and the inventory list, or excuse me, the customer order and the inventory list. The inventory list is what is currently available within the current inventory, and then the customers represent a demand upon that inventory. And there are three main elements in this. It's the series of events and interrupts that represent the list of orders. This can be done using a database inside of Extend. And there are two types, both stochastic and deterministic. In the deterministic order generation style model, a list of X number of previous orders and specific information about those orders is loaded in, and multiple ConOps configurations can be measured against each other based off of a defined set of orders. This can also often be pulled from previous orders stored in an inventory system, looking at both seasonal variation and or product variation. In a stochastic system, the inventory system itself has a probability associated with each item inside of that inventory list. So each order being generated will then go look at the inventory system and see what is the probability of the order containing that inventory, and then that's processed through the concept of operations and looking at both improved system performance or for current steady state within the system. One of the parts, those are just the list of information. Subsequent to that is the to execute the stock pull request. So as the order comes in, the stock pull request is created, and to do that, once again, the query equation block is critical in that environment, and followed on with packaging and shipping. Once again, that's going to be the batch and or queue matching that's used to do that, to execute that. In search and detect models, there are once again, two types of data sets, both the target information, the search type, and probability of detect. In this environment, there are four main elements. You have to create the targets. This can once again be a stochastic or a deterministic set. In the stochastic set, a known set of targets in a known location are created, and the model, different ConOps are run against that stochastic or deterministic model with then different variances of performance based off of the different ConOps that have been set up. In the stochastic environment, a random set of targets are created, and the current ConOps is then measured against a random set of targets. In the execute and search, the sequence of events and interrupts, once again, is going to be a database. In that list, in that case, the list of the sequence of events to execute that ConOps is then being stored, and then also the sequence of events, interrupts, is also being stored and will then interrupt the sequence of events. One of the things that has to be done is test for target. If the search and the target are in the same space, does the search find the target? This is often developed using model code within the query equation block, where the output of the query equation block can be the spawn that generates an item that triggers an event, or a value that gets carried through the simulation. And then a triggering target can be used during the preempt of an activity. One of the other things in model control is using the queue equation block. Similar to the query equation, in the queue equation is based off of rank equation, in which each item inside of the queue gets a rank result that's being stored for it. The winning rank, all of those outputs are then stored. They are stored for each rank. They are ordered by their rank, and then the winning rank gets the outputs published. There's a very unique situation in the queue equation block, and that's a rank value of blank. In the case where a rank value of blank is being stored, the item will not be allowed to leave the queue. This provides some high level of model versatility in allowing the queue equation to control what can leave the simulation. I'm going to show a demo of that. This was similar to the Excel-based load. A couple of things have been added to this model. The number of stations, we have 4 stations. The number of station time, also the number of available stations has also been added. In the model transfer sheet, we can see that the row, the column end on station data has been automatically updated to 3 because of this allowing us to insert and that automatically changing. In the model, the queue equation block is being used, and what is being set in the queue equation block is the database is checking to make sure that there is a quantity of station greater than 0. If that is the case, the rank in the queue is equal to that station number. With this queue being set the lowest the lowest rank gets highest priority. This pushes the order of operations to this pushes the priority to station 1 and the lowest station being 5. In the case where there is no station available, the I rank gets 0, and that does not allow any items to leave. I'm going to pause the simulation when the first item passes. And we'll notice that when the simulation pauses, the station quantity has dropped to 0. And this is done in this equation, which subtracts the number of stations from the current number of stations. Subsequently, when it's done processing, the same equation then adds the station back into being able to be used. Let's stop this model. One of the unique situations is if there are no stations of 1 available, we'll force this model into an ill condition. We'll run this model. Notice that it does not pause because no items could pass, and all of the items are currently waiting in the queue. None of them passed because of the 0 value that was being stored in station, thus forcing the item rank to be blank. One other thing that should be mentioned is measuring of utilization. In this case, the utilization on the stations is going to be of importance. And the way that's being measured is a read value. The read value is reading the quantity statement, and it is updating during a discrete event simulation, and it is reading every time the data source changes. In this situation, every time the data source changes, an updated value is placed out. Since utilization is a time-varying statistic, we are going to calculate the mean and variance using time-weighted statistics with an initial value of no value. In this situation, reset this. In this situation, we can select the station for which we would like information on. We can run the simulation, and we can get the results. Excuse me. We can run the simulation and get the results of a mean of 12. One of the things to keep in mind is, since this is presenting the average number of times that the queue is available stations, we are subtracting 1 from the number to get the utilization. We do not want how much it was available, but how often it was available, but we want how long it was being used in this calculation. Other ways of measuring inside of a ConOps model are with the rate library. In the rate library, the use of tank values to trigger events, not evenings, excuse me, i.e. running out of fuel. In this example, we have a tank here which contains 100 kilowatt hours of energy, and we can see that the indicators here are full, high, medium, and low. This indicator connector here can be used, will output these results, and as the tank reaches those values, these results get updated. So the indicator can be used to trigger, you have low energy, it's time to return, you're low on fuel, it's time to find a place to land, etc., etc. The other part of information is the valve block here. We can see that the valve block has a rate, which is the amount of energy divided by time, which in this case becomes power. In this case, we're going to measure the consumed energy, but it can be used to measure the consumed fuel, or any sort of consumed fluid or grouping where the individual elements are calculated as a rate. Here is a picture from a model that calculates the tool and service energy that's being processed over a certain amount of time. In this situation, the amount of tool and service power that is coming into this activity is being calculated. The addition block here is summing the math block here is summing the two inputs, and this is running the cum sum. In this case, a stop message is being used so that this does not trigger the event, but the trigger event is happening once the item passes through here. It's being triggered by this information block, and the total cumulative sum energy is being summed coming into this process, this activity. We have stopped both the incoming and outgoing messages, so the only item that triggers this equation is the item passing through this information block. If the item has processing time, it's going to be processed for a certain amount of time. Subsequently, on the exit, the same thing is happening. The amount of service and tool power are summed up, and once again, we're using an information block to trigger the calculation. This is the total power in and total power out. The total power out are being subtracted from each other, divided by 1,000 to convert watts to kilowatts, and we're looking at the power consumption through this rate block through a tank, an input tank, and an output tank. To kind of show the math, the valve block is is a rate divided by time, so the kilowatt hours divided by time, so it'll be the kilowatts. We're going to input in kilowatts, and the tank value integrates the valve block over time, so we integrate from model init to measure time of the kilowatt times time, and we get kilowatt hours at the measured time. So we can see that on the output side here, we have the kilowatt hours consumed at any one point in time, actually at the selected measurement time. This is one way to structure a electrical energy consumption model. One of the other things that allows are the gate blocks. Gate blocks are also one of the more powerful blocks inside of Extend. It allows for a chain of queues and activities and blocks to be grouped together so that only a certain number of items can be inside of this chain, thus allowing very complicated or very complex tools can be modeled using this, because you can use the gate block to represent the whole tool as there are multiple different options within that tool. In this case, dividing the number of areas. So in the gate block, we have two connectors. The first connector is the maximum amount allowed in the area, and the second connector on the output connector is the total amount in the area at any one point in time. By setting up a constant block and a divide block, and then also a mean and variance block using time-weighted statistics, the utilization of these items can be measured using these three blocks. This allows for chaining together multiple queues, multiple activities, multiple batch and unbatch blocks, and being able to measure the utilization across the whole system. This is a very valuable tool in building very complex representations of the real world. That's all I had. Dave, do you have any questions?
I did have a comment. There were some, please, first I want to mention, thank you very much, Brian. That was helpful. We don't tend to talk very much about these more advanced blocks, and it was useful to have someone show their actual use. So if there's any questions out there, please post them, and Brian or myself will answer them. There was one question about where you find these blocks. I believe someone had version 7. These are the query equation from the value library and the item library are new blocks in version 8. So you won't find them in version 7. It's also required that you have version ExtendSim AT. So they're not available in ExtendSim OR or ExtendSim CP either. So they're a more advanced block, and we put them in the advanced technology package, which is ExtendSim AT. Are there any questions? I don't see anything popping up here, but let's give it a moment. I did have a question. Ryan, do you have any specific instances where you've used these blocks in your modeling? Any specific problems that you've solved with them?
Right now, we are using the, and I will, excuse me, I will step back up. This consumed energy block right now is being used in a ConOps style model where the sequence of events is on the order of roughly 4,000 line items. The 4,000 line items were brought together. There were 4,000 line items. There were several hundred tools and several hundred services. They were brought together amongst 10 different users. So 10 different users were given subsets of an Excel spreadsheet to fill out and bring back to the architect, and then the architect then executed the model measuring the consumed energy across the current ConOps structure. This has been a very, very, very powerful tool in measuring the total amount of energy that's being consumed. One of the interesting comments back from the user community is this instantaneous ability to, at a specific measured time, measure the amount of consumed energy is a feature that they haven't had yet in their Excel-based models and in the other modeling tools that they've used. Using the gate block, this is something that I use all the time when building relatively complex representations of tools. In assembly sequences or in manufacturing sequences where a whole bunch of different steps have to happen in the same area, I use the gate block to represent that whole area and then use that to then measure, then use this utilization to then measure across that whole area. Also using the Q equation block to represent the amount of available stations. There have been, oftentimes, if you're modeling a situation where you have a furnace, for example, that can hold 1, 2, 3, 4, or 5 pallets into that furnace, this allows for staggered allocation of resources. So there's one furnace, but it can hold up to 5. The frames can hold up to 5. So you have built into it a frame, and that frame goes up 1 through 5, and subsequently then the furnace is represented by an item, by a resource. And so this allows for segregating a resource in that situation. So some of the places where I've used them in my modeling experience.
There are some questions here. Okay. I'll handle them out of order. Okay. Scott Burry from Dow, who was actually our, I think it was last month, he gave the master class, said that it's a good seminar. There's some comments about how to use these same blocks for generic modeling in a paper done by Naoko, and I'm not sure how to pronounce your last name, Akia. Scott, please correct me if I've mispronounced your last name. And you can find these at the 2011 Winter Simulation Conference archives. So that's a good point. So that's another bit of information about how to use these blocks. It's actually in a paper that was published at the Winter Simulation Conference. Of course, Brian, if you're willing to provide the slides and the example models, we have requests for those.
Oh yeah.
And the recorded session will be online as well.
Yep.
A good question was, how would you do this in version 7? So how would you use, for example, the equation query block, provide that same functionality before that block existed? It depends on exactly what you want the block to do. The basic case, you could write a loop in an equation block that went through and did all these calculations, but it would be it's a lot messier, a lot less convenient. There's also the spawning ability would be considerably more challenging because you'd actually have to have an item going in a loop, checking the condition, and then going through an unbatched block to spawn the item in that case. So these blocks, it isn't that you couldn't do it in version 7, but it would be considerably more complex. It would be about writing loops and equation blocks or loops of items going through there. Yeah, we did one more question. Can the blocks which input from Excel be made dependent on a variable or event?
Yes. One of the unique things about both the data import export block, and I'll pull up the original ones. Inside of the import export block, we have there are basically a couple of check boxes. Import at the beginning of a simulation is set up for an import, and one of the unique things about this is import at the first run of multi-run only. And this is a very, very important feature in 8. In R7, Dave and I went round and round on this, how to do this, and thankfully it's in 8. But one of the ways to trigger that is this connector. The input is import in. If this import at the beginning of the simulation is not checked, this import will not happen until that goes high. And so this import connector can be driven using any method, both equation value or an actual event inside of a model triggering either an information block that sends out a high to then initiate this. So there are other ways of driving inputs and outputs. You can do that from the input connector.
Another question that came up is, can you the import export block import from Access or SQL Server? They do have an ODBC driver, but a word of warning about ODBC, Microsoft seems to be dropping support for that, and we've had more and more of a challenging time getting that to work well. And that seems to be mostly related to the fact that Microsoft is not interested in supporting it in the future. In fact, you really have to hunt to make it work in Windows 7. You have to hunt for the, there's a little application that creates the data sources. That's not, it's kind of a nuisance to use. So I think we're going to go to a more modern method. Hopefully you'll see that in version 9, although we haven't done an awful lot of work on that yet. We are kind of putting our ducks in order to get that done with, I think it's ADO. Ken Cruz, who posted the question, probably knows more about that than we do. So if he has suggestions, I'd encourage him to contact us.
And Ken, I would also follow in that the reason why I focus so heavily on Excel and not the other methods is Excel is the most robust way to import, and converting other file types into Excel and then from Excel coming in. One of the other things that also this allows the user to go do is go execute macros in Excel that format and parse the data correctly so that the model architect can structure the data in the exact format that Extend needs to read it in.
I wanted to mention something else too on that. Also, it's a little bit of the squeaky wheel gets the grease. People, 90% or 95% of the requests for importing and exporting are to Excel. So we tend to focus on that simply because that's what the vast majority of people want. But we are interested in supporting specifically Access because that's kind of it may be a distant number 2, but it is certainly number 2. Well, I don't see any more questions, and it looks like we're about out of time. What is the maximum size of the Excel table that can be imported? We've tested against 1 million rows, and we do have customers that we have exceeded 1 million rows of import. So it's pretty good size. Probably going to be more limited by the memory on your computer than anything else.
And if you're working in Excel 2003, it's 62,000.
That's right. Yeah, so, there is a limit. Yeah. So we got to thank you for a good presentation. Yeah, there's a limit in older versions of Excel. That's correct. Yeah. Thank you very much, folks. I think we're done with this. Bryan, thank you for your time. I appreciate you taking the effort to put this together. I know you've got a busy week. And if people have other questions, feel free to send them to me, and I'll answer them directly or forward them to Bryan. So I hope everyone has a good day, and we'll talk to everyone later.
Thank you very much.